let's look at lecture 5. Now we're going to look at something called derived rules. This is a continuation of formal proofs. We have seen some set of rules and how to generate derivations out of those rules, and we saw some examples how we can prove statements using those rules and write derivations. Now we're going to see that these tasks of proving some theorem needs several subtasks and several kind of proof patterns you need to repeat again and again. So why don't we write them as a macro or derived rules and just do them in one shot and list them these extra rules along with our basic rules, and that would be very helpful in writing proofs. So we will go over some of those rules, and those rules will correspond to our intuitive understanding of reasoning that we are used to. So those ideas can be directly applied when you're writing proofs. First we will look at 4 such rules. One is called Modus ponens, second is tautology, third is contradiction, and fourth is contrapositive. Let's dive into it. So what is Modus ponens? Okay, so if let's suppose I give you that from sigma you can derive not f or g, from sigma you can derive f, then we can derive sigma derives g. Now this is fairly simple. You can see that this will sort of if f is true then not f is false, then you're left with g. But let's see how would you prove in our proof system. So we are given that this thing holds true, and this comes as a premise, and the other thing is that this also is a premise, so we write it as a premise. You can turn into an implication. Remember that this was part of definition of implication. Okay? We apply it on 1 and we get this f implies g. And we know that once we have f and this implication, then I can derive g, and then we obtain g. So this proofs let, okay, this 4 steps I can summarize as a one single big proof step, in which I am allowed to do this and this derives this. This proof rule will act like a first-class citizen as compared to the proof rules we saw in the previous lecture. Now we will not make any distinction that this is derived, this is not derived. Once you are derived, you can use it as you like. Okay, so let's see this rule in action. Okay? So you have this statement to be proven, and you have 2 things in the set and 1 thing needs to be proven. So you can see that this implication is sitting here, so it tells you that I can bring this q from left to right by introducing a q implication intro. So why don't I start with q being on the left side? So let's start with q being here. So I can derive by assumption this q. Now what we can do is we can also derive the other parts. For example, this one. Okay, we brought it out. Okay. Now we swap them because we're using symmetry. Now these 2 guys together look like a modus ponens candidate. So we apply modus ponens between them and we obtain P. Now we have P and this guy is yet to be brought out. So let's pull this one out. Okay. And if we pull this one out, so we get not P or R. So we are left with again modus ponens situation, and we get R. And then now we have proven P and R, so we can just apply intro conjunction and we obtain P and R. Now all we need to do pull this one out, which can be done via implication intro, and we got this proof. So now we have proven the statement that we wanted, and if we did not have modus ponens immediately ready with us, getting this out from here, these 2 will have a few number of steps additionally. So your proof would have been slightly longer, now it's slightly compact. So that's the benefit having these derived rules. Now let's look at more of these, and I will try to motivate these rules with common phrases. So let's see one. Okay, tautology. What is a tautology? When something is always true and said in a very complicated way. For example, I run when it rains or when it does not. That means I run always. So something always happens and you're just saying in some contrived way. What is equivalent in our setting is it is equivalent to setting that if I have this set sigma, can always prove that for any formula f, okay, not f or f. Okay? So how are we going to prove it? We can easily see that this situation is true because of assumption rule. F is left hand side, so I can derive f on the right hand side. Now what I can do is by applying implication intro, I can bring this f out on the right hand side. So we can always prove f implies f. Now we can do what? Def rule in implication, and we get not f or f, and we are done. We can have a proof rule. We can, out of the blue, we can always introduce not f or f, okay, for any formula. Okay, contradiction. Okay, if I eat, what is a contradiction? When the situation is like that, it's immediately false. For example, if I say I eat a cake and not eat it at the same time, that means this is absurd, and then sun is cold. Right? So what it's trying to say here is that once you introduce absurdity in your system, which is left hand side is absurd, then you can imply anything. Okay, and that's what needs to be proven. If you assume a contradictory thing to be true somewhere, then you have no reasoning left. Everything is true. It's often very counterintuitive why this will happen, but false implies everything. Okay. So let's suppose I have a contradiction available to me, f and not f, and then I can derive anything. Give me any formula, I will derive it. Okay. So let's see how that actually happens. Okay. So again, we need to premise, we need to assume that we are able to do this. So f and not f. So what do? You by symmetry bring it home other way around, not f and f. You apply lm, then you get not f out, and by introducing or intro, you can just simply say not f or g. Now what we can do is that this we obtain by applying and lm on this thing. Now we have f, we have this guy. Now we can apply modus ponens, I guess, and we obtain g, and that's what our code was. Okay, so you basically g is coming out of the blue. G came out of the blue here, and suddenly we were able to derive it. And therefore, once you dabble with absurdity, then there's no limit to conspiracy theories. That's the essence of logic. Okay? So we can turn this into a contradiction rule. Okay, contra rule. Okay, so let's see another trick we often use, which is called contrapositive. Okay, so this is a famous saying by Descartes. This is a philosopher who came up with this statement: "I think, therefore I am." In the process of proving existence of God by just using the structure of logic itself. This was an amazing effort he made. He wrote very long books and he was very excited about it, but well, of course, it was wrong. So you can write the same statement in the following way: I am not, therefore I do not think. It's just negating right hand side and putting on the left, and negating the left hand side and putting on the right. Okay, and it means the same thing, which we do all the time in our daily reasoning. So let's see, that kind of reasoning should also be allowed in our proof system. Again, our proof system doesn't imply such a thing. It does. Okay, so let's see. So if you have this situation that you have proven sigma union f proves g, then you should be able to prove that sigma union not g, which is like the right hand side came in the left hand side, proves not f. Okay, so let's see how can we prove it. Okay, so you have a sigma union f proves g, you do. I mean, you can just use double negation. And look, first time you're using double negation. So you introduce double negation, you got G. Okay. So you can push F out right hand side, then F implies not of G. You can introduce def of implication and write not F or not of G. We apply symmetry and then becomes not of G or not F. Now if we apply definition of implication, then in a reverse direction, so not G implies not of F. Recall that if this had been G, I could not have applied it. But now since I have taken it as a not of G, it gives me the ability to apply this definition. And please note that this kind of tricks you need to observe such that you can do the proofs. Now you have a not of G implies not of F. Now what do we do next? So we can introduce not G in the left hand side, which is we can always introduce anything on the left hand side. This is monotonicity. Okay, I like to. So what we can do, we can derive not G outside. Okay, since we have not G here, then I can derive not F. Okay, so we got this. If we have a left hand side, we have not G, we can always derive not F, and we are done. So therefore we have contrapositive rule available to us. So what I suggest is look at this proof. It has a lot of steps. A lot of steps are simple symbol pushing, and there is some insight some point of time where idea was captured, then things can be moved around, and try to identify where does this happen and how this proof holds together.